Hello everyone, welcome back to the channel. So today I would be also covering another problem, like another concept I would say. So this concept is actually you would have dealt with this regularly, like many problems you have solved around this particular concept only. So let's jump into discussing the particular concept. So the concept that would be talking about is LCA, right? I'm sure you all have done LCA and you also would be knowing that what is new in this. So it's something like lowest common ancestor, right? You must have all of this, solve this problem. I'm just here trying to give you today how to find the LCM, like, and with a modification as well, that how the question is being asked and how do we actually find this problem very optimally. Most of you would be doing some kind of a, okay, so like let's discuss this with the example only. So let's suppose we are having a tree, this particular 4. Let's suppose 2 is having 5 and 6 and 4 is having 7. So my simple question is, if I ask you the LCA between 3 and 6, so what you would be doing is it would be 1. So you would be going to the parent of this, and you would be going to the parent of this, and where they all both meets, you would be saying that this is my LCA. Yeah. So generally we do this particular thing, and this would end up getting a big of n complexity, I would say, because worst case it would be that you would be taking a skew tree and then you would be hopping upon and solving the problem. Now what if I tell you, like in this also you would be trying to maintain some space as well of finding the subtree, like storing the parents as well. Yeah, so you would be doing some this kind of stuff, right? So what I will be doing is I will be giving you two concept, like a concept of actually finding this problem very easily, and you will find it very good as well, like from my experience that you would be finding this very cool as well. Like a small prerequisite, watch the previous video, which is on Euler's Tour, right? This would give you a better jinx of how do we actually be solving this problem. So I'll give you a simple intuition. What we'll do is we'll store the complete path of this particular graph, like we'll traverse this particular graph and we'll store the tour of this particular graph as well as the height of each of the particular node. So let's suppose the height of particular node 1 is 1 over here, so 2 would be height at of 2, 5 would be at a height of 3, right? So the path would also be like 1 to 2, then 2 to 5, then 5 to 2, 2 to 6, 5 to 6, 2 to 1, 1 to 3, 3 to 1, 1 to 4, 4 to 7, 7 to back 4, 4 to back 1. So let's make a table out of it. So if we make a table, so let's store the vertices. So vertices would something be like 1, 2, 5, 2, 6, 2, 1, 3, 1, 4, 7, 4 and 1. So this is how your vertices would be. And if we write the heights as well, so it would be 1, 2, 3, it would be 2, 3, sorry, not 2, 3, so like 6 would be at 3 at, so 6 again would be 2, 1 is at 1, 3 at 2, 1 at again 1, 4 at again 2, 7, 3, 2 and 1. So this is how your table would look like. Now here is a simple intuition, or I would say a simple mathematical logic behind it. If I ask you, go and find the LCA between 2 and 4, or between LCA between 1 and 7, right? So what I'm claiming is it would simply be the range between 2, 4 and the 7 is here. In this particular range, the value with the least height would be your LCA. Now you all would be thinking that how is it like a optimized thing? So like here also we are taking big of n time. Why don't we are using the original approach? yeah, like this is a good question that you could ask me. This is a very good question that you could ask me. The simple reason why this approach is good, or when it is good, is when you are doing some kind of a range stuff or kind of a thing. Range stuff is like I'm giving you some kind of a queries. I'm giving you Q queries to go and find the LCA between 2, 7, right? So if each query is taking big O of n time, right? If each query is taking big O of n time, so it would be landed up to big O of Q1 time. And here you could actually optimize this particular time if you know the range between that, in which range you have to search the element, and you need to just find the minimum element in a particular range. So here you could actually optimize this particular stuff. So this is why this particular approach is good when you're dealing with some kind of a queries or stuff. So you could use this kind of a approach, right? And let's give you a particular modification as well. I'm sure many of you would be familiar with this particular modification, but yeah, let's discuss for the sake of the knowledge. Okay, so now here we are talking about the LCA between 2, 4, or like any kind of a stuff. Now what if I ask you, find me the let's erase this thing. Yep. So now let's suppose you need to find the kth ancestor. Okay, so let me explain you the kth ancestor. So here what we are talking about is, that if we want to go and find the ancestor for 2, 4, so 2, 4, here 1 would be the first ancestor, right? If we talk about 5 and 6, so 2 is their first ancestor, 1 is their second ancestor, right? In a similar fashion, you need to go and find me the kth possible, what would be the kth ancestor of two nodes u and v. If I give you this particular question, so if you would be going with your same approach of finding that logic, it would take a big of n time, right? And if I give you q queries to find this particular thing, so your time complexity would be big of n into q, right? And you know that this won't be an acceptable approach, right? This won't be an acceptable approach. So what we would actually be doing is, what the time complexity that I would be claiming is big of q into log n, that we could actually optimize this into big of q into log n. I'm sure if you would be following this channel, you would be knowing that if we talk about the optimization part, we only think about the pane area, right? What exactly our pane area is. So if we talk about the pane area, so our pane area is to find the kth ancestor optimally, right? We need to find this very thing optimally. So this is actually our pane area is. Okay. Now let me give you a analogy of how do we actually be thinking of to optimize this particular thing. If we talk about the kth ancestor, can I write this k as some 2 to the power i1 plus 2 to the power i2 till 2 to the power some value of im? Like I could write in the 2th power, right? I can break this k into some values of 2 to the powers, right? So if let's suppose, I'll give you an example. Let's suppose k is equals to 13. So we could actually break into 2 to the power 3 plus 2 to the power 2 plus 2 to the power 0. It would be 8 plus 4 plus 1. So we could definitely break it into the same fashion. Okay, and now let's assume that we have some kind of a dp. Let's not give you a dp term right now, like you would think that it would be a dp term or something. Let me tell you, if you need to find the 2 to the power kth ancestor, what if I tell you, go and find the 2 to the power k minus 1th ancestor and again go for 2 to the power k minus 1 steps. If you need to find the 2 to the power kth ancestor, right, go and find for 2 to the power k minus 1 and then do the 2 to the power k minus 1 steps again, right? Okay, so if we talk about this particular thing, let's give you a array, let me give you this particular analogy. So this would be telling you okay, so if I talk about up of u comma k, so this would be giving you the kth ancestor of u. So if we talk about the base case of this particular thing, so if we talk about the base case of this particular thing, so it would be, so it would be the first ancestor, right? So how do we find the 2 to the power ith ancestor, right? So we could simply break it to u of I, and I would simply write is that we need to find the k minus 1th, right? So we could simply write it as I minus 1, then again find for I minus 1. So this is how our net dp state kind of, or dp transition you would say something would look like. And if you go with this particular logic, you have already stored the 2 to the power ith ancestor of a particular node. So if you want to go and find for the 13th ancestor, right, 13th ancestor, you will first go to its 2 to the power 3rd, which is the 8th ancestor, then you will go and find for the 4th, like jump to the 4th from 8 and then again jump to the first ancestor of that. So this kind of binary jumping, like we are doing some kind of a binary jumping, right? This kind of doing a binary jumping is actually called as binary lifting. This is actually called as binary lifting. I have not given you this term pre-hand so that because many of you would think that what exactly is binary lifting and all. So it's nothing, that it's a simply normal, I would say, a state that where you have broke a particular problem into smaller sub problem of how do we actually solving this, and this whole concept is known as binary lifting. I'll give the code of this in the comment section, so you would be able to see the code as well. So this is how the binary lifting and the LCA problem is look like. So here we have discussed two kind of concepts, and I would recommend you to go and try this particular concept to find the kth ancestor, and I'm sure you would be able to do this very faster and very cleanly and very in a very optimal fashion. And if you like the channel and if you feel that I should make more videos on this particular concepts, covering more concepts, do let me know in the comment section, and do like, share and subscribe the channel. Thank you everyone.